If modern agriculture is the most technologically advanced system in human history, why are we talking about water shortages every single year? Think about it. We have satellite-guided irrigation mapping. We have variable rate pivots that adjust application down to specific zones. We have moisture probes, evapotranspiration models, drone imagery, AI-driven yield forecasting. Billions of dollars in equipment, analytics, infrastructure. And yet aquifers are dropping. Reservoir levels fluctuate more aggressively than ever. Farmers across multiple regions are being told to reduce usage, switch crops, or prepare for allocation limits. That contradiction matters, because either nature suddenly changed the rules, or we engineered a system that leaks water at scale. Globally, agriculture accounts for roughly 70% of freshwater withdrawals. In many irrigation systems, field-level efficiency still sits between 50 and 65%. That means a significant portion of pumped water never benefits the crop in a meaningful way. It evaporates before infiltration. It runs off before absorption. It percolates beyond the root zone, carrying nutrients with it. Then we respond by drilling deeper wells or increasing pump capacity. That's not resilience. That's escalation. Now pause and consider something uncomfortable. There were civilizations farming in deserts long before diesel engines, long before electric motors, long before PVC pipe and center pivots. And they sustained agriculture not for one generation, but for centuries. So either they were incredibly lucky, or they understood water physics in a way we stopped prioritizing. This video is not nostalgia. It's not romanticizing the past. Ancient farmers also failed in many places. But some irrigation systems lasted for hundreds, even thousands of years. That level of durability deserves examination. Because modern irrigation is optimized for throughput, ancient irrigation was optimized for balance. And balance may be the missing variable. Let's define the real issue. Water scarcity is rarely about absolute absence. In most agricultural regions, total rainfall across a year is not zero. The problem is timing, retention, distribution, and loss. Modern irrigation tries to solve timing by overpowering it. When rain doesn't come, pumps compensate. When soil dries, more volume is applied. When yields plateau, water input increases. But every time we increase delivery speed, we also increase loss pathways. Evaporation increases when water sits exposed under high heat. Runoff increases when application rate exceeds infiltration rate. Deep percolation increases when soil structure is degraded or compacted. Modern systems often treat soil as a medium to pass water through. Ancient systems treated soil as a reservoir. That philosophical difference changes engineering decisions. Let's talk about energy. Most large-scale irrigation today depends on pressurized systems. Pumps lift water from deep aquifers or move it long distances across flat terrain. That requires fuel or electricity. The deeper the well, the higher the energy demand. As aquifers decline, lift distance increases. Energy cost increases. Maintenance increases. Financial risk increases. Ancient irrigation systems were built around gravity whenever possible. Gravity does not require diesel. Gravity does not fluctuate with market prices. Gravity does not break down. When systems are gravity-fed, operational cost after construction drops dramatically. That matters in long-term sustainability models. Now let's talk about evaporation. Open canals in hot climates can lose significant volumes of water before it ever reaches the field. Surface flood irrigation increases exposed surface area even more. In arid regions, high solar radiation accelerates evaporation loss. Ancient engineers understood something simple but powerful. Water exposed to sun disappears faster. So in multiple civilizations, water was transported underground or shaded whenever possible. Modern systems often prioritize convenience and scale over exposure control. Scale wins in the short term. Exposure control wins in the long term. And then there's runoff. Modern fields are often graded for efficiency. Large flat expanses allow mechanization. Drainage tiles remove excess water quickly to prevent waterlogging. All logical decisions for productivity. But when water leaves quickly, infiltration time decreases. When infiltration decreases, groundwater recharge decreases. When recharge decreases, aquifer stability weakens. We've engineered speed into the system. Speed increases productivity. It also increases loss. Now let's introduce the core thesis of this entire series. The water crisis is not just about supply. It's about design bias. Modern irrigation is biased toward maximum extraction and rapid distribution. Ancient irrigation was biased toward controlled flow and maximum retention. One model depends on continuous energy input and infrastructure expansion. The other depends on terrain, gravity, and soil physics. Neither is perfect, but only one lasted for centuries without fossil fuels. Before we examine specific ancient systems in the next sections, we need to shift perspective. Instead of asking, how do we deliver more water efficiently? We should ask, how do we keep water on the land longer? Retention changes everything. When water infiltrates slowly, soil moisture remains stable longer. When moisture remains stable, crops experience less stress. When stress decreases, yield variability decreases. Modern agriculture often compensates for instability with inputs: more fertilizer, more irrigation cycles, more chemical management. Ancient systems compensated with structure. They shaped the land to manage flow. They aligned channels with slope. They matched extraction rates to recharge capacity because their systems physically could not exceed natural limits. That physical limitation enforced sustainability. Modern pumps removed that limitation. When you can extract faster than recharge, depletion becomes inevitable unless managed carefully. And management requires discipline, regulation, or voluntary restraint. Ancient gravity-fed systems built restraint into the design itself. That may be the most important lesson. Technology gave us power. It did not guarantee wisdom. In the next part, we're going underground to examine one of the most durable irrigation innovations in history, a system built in arid landscapes that still functions in some regions today. No electricity, no pumps, no evaporation losses across miles of open canals. Just gravity, slope, and engineering precision. If you think water problems are new, wait until you see how old the solutions are. 2,000 years ago, farmers in what we now call Persia faced a problem most modern producers would consider unworkable. Low rainfall, extreme heat, high evaporation rates, long dry seasons, no diesel engines, no electric pumps, no steel pipelines, and yet they built agricultural systems that survived for centuries. Not decades, centuries. The solution was called the Qanat. At first glance, it doesn't look revolutionary. It's just a tunnel, a gently sloping underground channel connecting a mountain aquifer to farmland below. But that, just a tunnel, mindset is exactly why it's genius. Here's how it worked. Engineers would identify a reliable aquifer at higher elevation. Then they would dig a horizontal tunnel, often several kilometers long, with a very slight downward gradient. Along the way, vertical shafts were drilled to the surface at intervals. These shafts allowed ventilation, debris removal, and maintenance access. Water flowed purely by gravity. No pressurization, no pumping, no mechanical lift, and because the water traveled underground, it was protected from direct sunlight. That dramatically reduced evaporation loss compared to open canals. Think about that in modern terms. In hot agricultural regions today, evaporation from open conveyance systems can represent significant loss before water ever reaches the field. Surface storage reservoirs lose even more during peak summer heat. The Qanat system eliminated most of that exposure. But here's the deeper brilliance. Flow rate was naturally limited. The slope of the tunnel and the recharge rate of the aquifer determined how much water could move through the system. Farmers could not suddenly double extraction because market prices were high that year. The physical structure prevented overpumping. Restraint was built into the engineering. Compare that to a modern deep well with a high-capacity pump. If commodity prices spike, there's a strong incentive to irrigate more acreage or increase application frequency. With sufficient horsepower, extraction can exceed natural recharge for years before consequences appear. And when they do appear, it's in the form of declining water tables. The Qanat system avoided that trap by design. Now here's the part that should make modern engineers pause. Many Qanats operated continuously for hundreds of years. Some still function today in parts of the Middle East and North Africa. That's durability. Modern irrigation infrastructure, by contrast, requires continuous maintenance cycles, energy input, part replacement, and capital reinvestment. Pumps fail, motors burn out, fuel costs fluctuate, regulations change. Qanats required labor to build. Once constructed, operational costs were minimal. It was front-loaded investment for long-term stability. Modern irrigation often operates as ongoing operational expenditure. Different philosophy, different risk model. Let's talk about water quality. Because Qanats pulled from aquifers and transported water underground, contamination risk from surface pollutants was lower. Sediment loads were reduced, temperature fluctuations were minimal. Cooler water also reduced evaporation once it emerged near fields. Now imagine applying that principle to today's water-stressed regions. What if instead of prioritizing higher capacity pumps, we prioritized passive flow systems wherever terrain allows? What if irrigation districts redesigned portions of distribution networks to use gravity gradients more aggressively? What if groundwater extraction was physically capped by infrastructure design instead of solely by policy enforcement? The Connaught system teaches a core lesson. When engineering respects natural limits, sustainability becomes structural rather than regulatory. Modern agriculture often relies on regulatory frameworks to prevent overuse. Allocation limits, pumping restrictions, water rights negotiations. Ancient systems embedded those limits physically. You couldn't overdraw because the system wouldn't allow it. Now let's confront a common objection. Ancient systems worked at smaller scale. True, population density and production intensity were lower. But scale does not automatically invalidate principle. Gravity still works. Evaporation still happens. Recharge rates still matter. Physics has not updated its operating system. Another overlooked advantage of Connaughts was distributed access. Water outlets were spaced along the tunnel's exit zone. Communities shared access according to pre-agreed schedules. Because flow was steady but limited, allocation required cooperation. Steady flow changes management behavior. Modern high-volume systems encourage peak usage behavior. Apply heavily when needed, drain quickly, refill later. Steady, limited flow encourages planning. Planning encourages soil stewardship. When water arrives at predictable, moderate rates, irrigation strategies adjust accordingly. Cropping systems evolve around availability rather than forcing availability to match crop ambition. This matters today more than ever. In regions facing aquifer depletion, the instinct is often technological escalation. Deeper wells, stronger pumps, larger infrastructure, but escalation does not change recharge rate. Connaughts aligned extraction with recharge automatically. That alignment is the real innovation. Now imagine combining modern monitoring tools with ancient structural wisdom. Picture a system where groundwater levels are tracked digitally, but extraction is limited by gravity-fed infrastructure that physically matches average recharge capacity. Technology for awareness, design for restraint. That hybrid model could dramatically reduce long-term depletion risk. Because here's the uncomfortable truth. Modern irrigation gave us control. But control without constraint becomes exploitation. Ancient Persian engineers built constraint into control. And that is the difference between a system that lasts 30 years and one that lasts 300. The lesson is not to abandon modern pumps entirely. It is to question whether unlimited extraction capability should be the default. The Connaught system forces us to ask a hard question. If a civilization without fossil fuels could maintain stable irrigation for centuries in arid conditions, why are modern aquifers collapsing under our watch? In the next part, we move to another civilization that mastered water distribution at scale without mechanical pumping. They didn't just move water long distances. They mastered slope, pressure, and redundancy with obsessive precision. And what they understood about slow flow may be exactly what modern irrigation forgot. When people hear about Roman water engineering, they picture postcard arches, tourists, selfies, ruins, but the real power of Roman hydraulic systems wasn't aesthetic, it was control. Across the territory of the Roman Empire, engineers built aqueduct networks that transported water over vast distances using nothing but gravity and mathematical precision. No pumps, no pressurization plants, no electric assist, just slope. And here's what makes that remarkable. The gradient in many Roman aqueducts was often less than 1 meter per kilometer. That level of precision without modern surveying equipment is borderline obsessive. Why so careful? Because water velocity determines everything. If flow is too fast, erosion increases. If flow is too slow, sediment accumulates. If slope is inconsistent, structural stress develops. Rome didn't just move water. They managed energy within the water. Modern irrigation often prioritizes delivery rate. Gallons per minute, acre-feet per hour, coverage efficiency per cycle. Roman systems prioritized stability of flow. That difference changes outcomes. Water that moves at moderate velocity infiltrates better when distributed. It causes less erosion. It creates predictable distribution pressure. Roman aqueducts fed into holding basins, cisterns, and branching distribution channels. The system wasn't one giant high-pressure line feeding everything at once. It was tiered, redundant, distributed. If one section failed, others could continue operating. Flow was modular. Now compare that to a modern irrigation district dependent on centralized pumping stations. One power outage, one mechanical failure, One regulatory disruption, the whole chain stalls. Roman engineering assumed failure was inevitable and designed around it. Modern irrigation often assumes uptime. That's a risk profile difference. Let's talk about runoff. In many modern agricultural systems, fields are engineered for rapid drainage. Subsurface tile drainage removes excess water quickly to prevent root damage. Surface grading ensures uniform irrigation coverage. It's efficient, but it accelerates water exit. When rainfall hits, much of it leaves the field rapidly. When irrigation exceeds infiltration rate, runoff increases. That water doesn't disappear. It moves downstream, often carrying nutrients and sediment. Rome understood something subtle. Water that stays longer benefits more. Their distribution systems slowed water before use. Basins allowed sediment to settle. Flow rate dropped before final allocation. Slower water increases infiltration potential. Infiltration increases groundwater recharge. Recharge stabilizes long-term supply. Modern systems often treat recharge as incidental. Roman systems treated storage and stabilization as intentional. Now here's the uncomfortable pivot. Modern agriculture has optimized for peak yield per season. Roman water engineering optimized for longevity of supply. Those are not the same objective. Peak output encourages maximizing throughput. Long-term stability encourages moderating throughput. If your system is designed for maximum seasonal extraction, depletion becomes a management problem. If your system is designed for equilibrium extraction, depletion becomes structurally difficult. That's the philosophical divide. Now let's bring this into today's context. Many aquifer-dependent agricultural regions face declining water tables because extraction exceeds recharge over extended periods. Regulation attempts to manage this imbalance through policy, quotas, pumping limits, allocation frameworks. Policy requires enforcement. Design enforces itself. Roman aqueduct systems were limited by gravity and slope. You couldn't suddenly triple the flow because wheat prices spiked. The infrastructure would not allow it. Now imagine if modern irrigation infrastructure incorporated physical recharge-based constraints, not just legal ones. Imagine if distribution capacity was calibrated to sustainable yield rather than maximum pump horsepower. That would shift the incentive structure entirely. It would force cropping decisions to align with hydrological reality instead of market volatility. That's a radical idea in modern agriculture. But Rome operated under hydrological reality because they had no alternative. Let's examine another overlooked factor, maintenance culture. Roman aqueducts required constant inspection. Channels were cleaned, structural integrity was monitored, community responsibility was embedded into the system. Water wasn't treated as an infinite commodity. It was treated as a shared asset. Modern irrigation often treats water as an input variable. Input variables are adjusted based on need. Shared assets are protected based on continuity. That mindset shift matters. And here's where retention tightens. We've talked about Persia and underground restraint. We've talked about Rome and slope precision. Both civilizations engineered systems that slowed water down. Now ask yourself, what does modern irrigation reward? Speed, high-capacity pumps, rapid coverage, quick drainage, fast turnover. Speed increases operational flexibility. It also increases volatility. Because fast systems respond quickly to stress, but they also amplify mistakes quickly. Apply too much water? Runoff spikes immediately. Underestimate evapotranspiration? Stress appears fast. Rely on energy input? Fuel price changes hit instantly. Slow systems dampen shocks. Rome engineered dampening. Modern irrigation often engineers responsiveness. Responsiveness is powerful. Dampening is resilient. In a stable climate, responsiveness works. In a volatile climate, dampening protects. Now consider the water crisis narrative. We're told the problem is insufficient rainfall or climate variability. Those factors matter, but if your infrastructure is built around rapid extraction and rapid exit, variability hits harder. If your infrastructure is built around moderated flow and retention, variability impacts are softened. Rome survived drought cycles. They survived infrastructure damage. They survived political instability for centuries while their water systems kept functioning. Not because they were lucky, because they built with limits. In the next part, we move to a region where gravity alone wasn't enough. Where slope was extreme, rainfall unpredictable, and frost a constant threat. High in the Andes, engineers didn't just manage water. They reshaped entire mountainsides to control it. And what they achieved without steel or concrete might be the most relevant lesson for soil and water retention today. High in the Andes, long before steel tools or diesel engines, farmers faced a brutal equation. Thin soils, steep slopes, unpredictable rainfall, nighttime frost, intense solar radiation during the day. By modern standards, it looks like marginal land. And yet the civilization of the Inca Empire turned mountainsides into stable agricultural zones that fed millions. Not by overpowering nature, by reshaping terrain to cooperate with it. The Andean terrace system was not just erosion control. It was hydrological engineering layered with thermal regulation. Let's break it down. Terraces slowed water. That sounds simple. It isn't. When rain falls on a steep slope, gravity accelerates runoff. Fast runoff means less infiltration. Less infiltration means lower soil moisture retention. Lower retention means higher crop stress. Terraces interrupt slope length. Shorter slope segments reduce velocity. Reduced velocity increases infiltration time. Increased infiltration improves soil water storage. Now add stone retaining walls. Those walls absorbed heat during the day and released it at night. That buffered temperature swings and reduced frost damage. In other words, terraces didn't just manage water. They engineered microclimates. Modern irrigation typically reacts to climate variability by adding inputs. If temperatures spike, apply more water. If drought persists, increase irrigation frequency. If frost threatens, deploy energy-intensive mitigation systems. The Inca engineered landscape features that reduced volatility before inputs were needed. That is preemptive resilience. Now think about soil structure. Terrace construction often included layered profiles. Coarse material at the base for drainage. Finer soils above for root development. Organic matter incorporated for moisture retention. This wasn't accidental stacking of dirt. It was intentional water staging. Water infiltrated slowly, drained gradually, and remained available within the root zone longer. Modern irrigation often compensates for poor soil structure with increased water application. Terraces improved structure first, then optimized water use. That sequencing matters. Fix structure, then manage flow. Modern systems often reverse it. Manage flow aggressively to compensate for structure degradation. Now let's talk about retention versus delivery. Modern irrigation conversations focus heavily on delivery efficiency. How precisely can we apply water? How evenly? How quickly? The Andean system focused on retention efficiency. Once water entered the system, how long could it be held? That question is almost absent from mainstream irrigation metrics. Because retention doesn't show up as easily in pump output charts. But it shows up in drought tolerance. Fields that retain moisture deeper in the profile require fewer emergency irrigation cycles. Crops with consistent moisture gradients experience less stress volatility. Roots grow deeper when moisture persists. Terraces also reduced topsoil erosion dramatically. In steep environments without terraces, heavy rain strips nutrient-rich layers downhill. That reduces productivity over time. By flattening slopes into steps, the Inca reduced kinetic energy in flowing water. Soil stayed in place. Nutrients remained local. Modern high-volume irrigation events can replicate erosion dynamics if infiltration rate is exceeded. Especially in degraded soils with compaction. The Andean system was built to avoid high-energy water events. Slow, layered, controlled. Now here's the key insight. The Inca did not have the option of drilling deeper wells. They had to work with rainfall and natural springs. Because extraction options were limited, optimization focused on maximizing what entered the system. Modern agriculture often treats water supply as expandable. Deeper wells, larger reservoirs, extended conveyance, expansion mindset. The Inca operated under constraint mindset. Constraint forced innovation in terrain shaping. And that terrain shaping produced resilience. Now let's bring this forward. Imagine applying terrace logic not necessarily as mountain staircases, but as contour-aligned water management systems in modern fields. Swales that follow elevation lines. Micro-berms that slow runoff. Contour planting that reduces flow velocity. On-field retention basins that capture peak rainfall and allow gradual infiltration. These aren't medieval concepts. They are physics-based hydrology. But they require one thing modern mechanized farming often resists: irregularity. Terraces interrupt uniformity. Modern large-scale equipment thrives on uniform flat expanses. There's the trade-off. Uniformity increases machine efficiency. Landscape modulation increases water efficiency. Which one dominates long-term sustainability? That depends on how scarce water becomes. And here's the retention trigger. In many water-stressed regions today, rainfall totals have not collapsed dramatically. What has changed is distribution. more intense rainfall events, longer dry gaps between storms. Terrace logic handles intensity better. Short, intense rainfall bursts on flat, compacted land create runoff spikes. On stepped, slowed systems, intensity is absorbed incrementally. The Inca engineered shock absorbers into the mountain. Modern irrigation often operates like a rigid system. Rigid systems crack under volatility. Flexible systems bend, and terraces were flexible hydrology. They allowed excess water to be staged, infiltrated, and distributed across time. That time dimension is critical, because water scarcity is often a timing mismatch. Too much at once, too little later. Terraces compress that mismatch. Now connect Persia, Rome, and the Andes. Persia moved water underground to prevent evaporation and enforce extraction limits. Rome mastered slope to stabilize flow and build redundancy. The Inca reshaped mountains to increase retention and moderate climate stress. Different geographies, same underlying principle. Slow water down. Respect limits. Design for centuries, not seasons. In the final part, we're going to bring this into the present. We're going to confront the uncomfortable idea that modern irrigation may not be failing because it lacks technology. It may be failing because it lacks restraint, and the next generation of water-stable agriculture might not come from bigger pumps. It might come from re-engineering how land holds water in the first place. Let's stop pretending this is only about drought. Yes, rainfall patterns are shifting. Yes, temperatures are rising in many regions. Yes, pressure on aquifers is increasing. But those are stressors. Stress reveals weakness. It does not create it. If your irrigation system collapses under variability, the issue is not only climate. It's design exposure. Over the last 4 parts, we examined 3 civilizations separated by geography, culture, and time. The underground gravity systems of ancient Persia. The slope precision distribution networks of the Roman world. The terrain-engineered terraces of the Andes. Different continents, different climates, same underlying logic. Water must be slowed. Water must be retained. Extraction must respect limits. Modern irrigation, by contrast, is optimized for throughput. Maximum gallons per minute, maximum acres covered, maximum seasonal yield. Throughput is not inherently wrong. But throughput without restraint creates dependency. Dependency on energy, dependency on infrastructure uptime, dependency on stable aquifer levels, dependency on cheap fuel. And here's the hard question. What happens when those dependencies strain simultaneously? The uncomfortable truth is that many modern irrigation systems are built on the assumption that extraction can always scale to demand. Ancient systems assumed demand must scale to extraction. That inversion changes everything. Let's break it down practically. Modern irrigation solves problems reactively. Soil dries? Apply water. Heat spike? Increase frequency. Yield target rises? Expand coverage. Ancient systems solved problems structurally. Increase infiltration depth. Reduce evaporation exposure. Match withdrawal to recharge. Stabilize microclimate. Reactive systems require constant adjustment. Structural systems absorb variability. Now imagine a hybrid model. Not abandoning modern technology, but integrating ancient principles into modern frameworks. Picture this. Fields designed along contour lines to reduce runoff velocity. Strategically placed retention basins capturing peak rainfall. Gravity-fed distribution networks wherever topography allows. Application rates calibrated to infiltration capacity, not pump maximum. Groundwater extraction physically limited to average recharge rates. Sensors and data analytics still exist, but they serve a system built on restraint, not expansion. That's the shift. Because let's be honest, many water crises today are not the result of absolute scarcity. They are the result of overextension. Aquifers decline because extraction exceeds recharge for extended periods. Surface reservoirs strain because seasonal storage is inadequate relative to usage. We expanded demand faster than recharge systems could handle. Ancient civilizations didn't have the option to overextend as aggressively. Constraint-shaped design. Now consider soil health. Water retention is directly tied to organic matter levels, aggregation stability, and compaction status. Degraded soils require more frequent irrigation because they cannot hold moisture effectively. Ancient terrace systems improved soil structure intentionally. Modern agriculture sometimes degrades structure, then compensates with irrigation volume. That is operational escalation, and escalation compounds risk. The future of water-resilient agriculture is not bigger pumps. It's better retention. Farmers who can hold moisture longer within their soil profile will be less exposed to allocation cuts, fuel volatility, and rainfall timing gaps. Retention equals independence. Independence equals resilience. Now let's address the elephant in the room. Scale. Modern farms operate at a scale ancient civilizations never faced. Global markets demand consistency. Mechanization requires uniformity. Economic margins are tight, true, but scale does not eliminate physics. Water still evaporates. Runoff still accelerates on bare slopes. Aquifers still decline when extraction exceeds recharge. Ignoring those realities because equipment is efficient is not strategy. It's optimism, and optimism is not a water management plan. The next era of irrigation innovation may not be about increasing precision alone. It may be about embedding physical limits into infrastructure, designing systems that make overuse difficult rather than merely discouraged. That sounds restrictive, but it may be the only way to ensure continuity across generations. Ancient engineers did not design for quarterly returns. They designed for civilizational survival, and their systems lasted because they aligned with hydrological reality. Modern irrigation has the advantage of data, material science, and advanced modeling. If we combine those tools with ancient restraint principles, the result could be extraordinary. High-tech monitoring layered onto low-loss distribution. Advanced soil analysis combined with contour-based water slowing. Recharge-aware extraction paired with precision scheduling. That is not regression, that is evolution, because the ultimate goal is not maximum water movement. It is stable water presence. Water that stays long enough to matter. Water that feeds crops without collapsing aquifers. Water that supports yield without demanding escalation every season. The farmers who win the next 30 years will not be the ones who can pump the most. They will be the ones who can keep the most. Keep it in the soil. Keep it in the profile. Keep it within recharge limits. 2,000 years ago, civilizations without engines built systems that balanced water across centuries. Today, with satellites and sensors, we struggle to balance it across decades. That contradiction should not be ignored, because the future of irrigation may not belong to the farm with the biggest pump. It may belong to the farm designed with the most restraint. And restraint, it turns out, is not weakness. It is engineering discipline. The question now isn't whether ancient irrigation secrets were impressive. It's whether we're willing to admit they might still be relevant.